So if you're building anything serious with LLMs right now, you know this feeling. You get everything working, it's powerful, and then you just hit a wall.
You hit the deployment wall. Yeah, it's the biggest point of friction when you try to go from, a cool research project to a real product.
Get this size mismatch problem.
Exactly. You've trained this amazing model. It's maybe 51 gigabytes of pure intelligence.
And then you try to run it on something normal, like an RTX 3090.
Or a 4090. A great card, but it maxes out at 24 gigs of VRAM. It doesn't fit.
So your beautiful 51 gig model is just a file. You can't run it efficiently, or maybe at all, unless you go buy these super expensive server GPUs.
And that really limits who can use the technology. Which brings us to the solution we have to talk about today, quantization.
Okay, so what is that exactly?
The best analogy I've heard is it's like JPEG compression, but for the AI's brain.
I like that.
Yeah, so you take a 50 megabyte raw photo, you can press it to a 5 meg JPEG. You lose a little detail, sure, but it looks pretty much the same.
And for an LLM?
You take that 50 gigabyte model and you shrink it down to maybe 13 gigabytes.
Oh.
That's a huge reduction. Yeah. And that makes it fit on all that consumer or, mid-range enterprise hardware.
Okay, that is a staggering reduction. But how do you compress the model's brain without making it, dumber?
That is the key question. The technique is very specific. It focuses almost entirely on compressing the model's weights.
And the weights are the learned knowledge.
The learned parameters, yeah. They're static, they're stored in the file, and they are most of the file size. But the activations?
Okay, what are those?
That's the data that's actually flowing through the network when the model is thinking, when it's doing the math. Those are kept at a much higher precision.
Ah, okay, so you keep the thinking part high quality.
Exactly. And that's why you see these slightly intimidating notations, like W4A16.
Right, I've seen that everywhere. What does that actually mean?
It's the standard for deployment now. It means the weights are stored in a 4-bit format. That's the W4, the high compression part. But the actual math, the activations, are done in 16-bit floating point, the A16.
So we get huge memory savings, speed boosts. What's the catch? Nothing in computer science is ever free.
The trade-off is precision. You are literally making the numbers in the model less precise.
And if you do that badly?
If you do it badly, the model starts to fall apart. It hallucinates, it produces gibberish. But if you do it well, the quality loss is so small that only a benchmark can detect it. The end user never notices.
Got it. And just to be clear, this is about model size and memory. It doesn't touch things like context length or token limits, does it?
No, not at all. Those are architectural things, totally separate. So when we look at how this is done, quantization really happens at two very different points in a model's life.
And I'm guessing one of these is for the huge research labs and the other one is for, well, the rest of us trying to get things working.
That's a pretty good way to put it. So path one is something called quantization-aware training, QAT.
Okay.
This happens during the training. From day one, the model is learning how to work with this low-precision math. It's basically learning to ignore the noise from the compression.
So it's built for compression from the very beginning.
Precisely. You'd use this if you're training a foundation model from scratch or doing a massive fine-tune. It's complex, it's slow, you have to change your whole training pipeline.
So who does this?
The big players. Meta AI, OpenAI, hardware companies. It gives the absolute best quality, but it's a heavy lift.
But for almost everyone else, we're talking about path two.
We are. Post-training quantization, or PTQ. This is where the democratization really happens.
Because it's simpler.
Much, much simpler. You take a model that's already trained, say a new Llama 3 you just downloaded, and you compress it after the fact, specifically for deployment.
So this is what you do when you're moving from your big, expensive A100 training server down to the hardware you'll actually use in production.
The 3090s, 4090s, L4s, exactly. It's fast, it's way less complex, and the quality gap between this and QAT. I mean, for most applications today, it's negligible.
Yeah.
PTQ is the indispensable tool for production. So for anyone listening who needs to get a model into production, like today, let's just lay out the default recipe.
Just shopping list. I like it. What works best right now?
The default setup you should start with is AWQ W4A16. So that's 4-bit weights, 16-bit activations, using the activation-aware weak quantization method.
AWQ. Okay.
And here's the crucial part. You have to use good domain-specific calibration data, maybe 128 to 512 examples, and you do all this in a completely isolated environment.
Okay, let's unpack that. Let's start with the environment, because I feel like everyone who's ever done this has lost days to weird version mismatch errors.
Oh, they will absolutely ruin your week, not just your day. So step one is environment isolation.
A separate virtual environment.
A completely separate one just for your quantization tools, things like Elm compressor or AutoAWQ. And this has to be separate from your inference environment, your VLLM or transformer setup.
And that avoids the dependency hell.
It avoids the GPU driver conflicts, the Python library nightmares, all the stuff that stops you cold.
Okay, step 2 was calibration data. You said it's not just blind compression anymore, it's data aware. What does that mean?
It's a really smart process. The tool watches how the model behaves on those sample inputs.
And it learns from that.
It learns which weights are the most sensitive, which ones, if you compress them too much, would just break the model's ability to reason. Then it knows to protect those critical weights.
And you don't need a massive data set for this, right?
No, not at all. 128 to 512 examples is usually plenty. But, and this is the tip that separates a good deployment from a bad one, the data has to be representative.
Meaning?
If you're building a legal model, you calibrate it with legal text. If you feed it random Wikipedia pages, it's going to optimize for the wrong thing and fail on the actual legal questions. Okay, so once you have the environment and the data, you have to actually pick the method. We said AWQ is the best practice, but there are really 3 major players you'll see in production.
Right. AWQ, GPTQ, and GGUF. Now, you said AWQ is faster and higher quality. So why would anyone still use something like GPTQ?
That's a perfect question. You should think of them as tiers. First, there's AWQ. That's the performance king for GPU deployment right now.
The gold standard.
It's the gold standard for high-performance servers, especially if you're using something like VLLM to serve it.
And then there's GPTQ.
GPTQ is your ultra-reliable fallback. It's been around longer, the ecosystem is more mature, and it just works with more models, especially older or more fringe ones.
So it's plan B.
It's plan B. It might be a little slower at inference, but it is rock solid. You use it when you hit compatibility problems or just need maximum stability.
And then there's GGUF, which I see everywhere for running models locally.
Right, and it's important to know GGUF is a file format, not a method like the others. It comes from the llama.cpp project.
And it's for?
It's the standard for running models on Apple Silicon, on your MacBook, on CPUs, on edge devices. For a pure GPU server, AWQ is usually better, but for anything local, GGUF is king.
So, to summarize, AWQ for servers, GGUF for local, and GPTQ as your fallback.
That's the playbook.
Okay, let's circle back to that W4A16 setting. We know W4 gives us that massive, like 75% size reduction. But why is the A16 part so important? Why not compress the activations too?
Because that goes right back to the function of the model. Think of the weights, the W4 part, as the model's static compressed library of knowledge.
Okay.
But the activations, the A16, that's the high precision calculator it uses to think about the current input. You can have a compact library, but you don't want a low precision calculator for the actual reasoning.
Ah, so the intelligence is in the quality of the calculation itself.
Precisely. That A16 means the critical math is still happening in the 16-bit floating point, just like it was during training. That's what keeps the model smart, even though its memory is compressed. It's the perfect sweet spot. So you've picked your method, you run the process, it takes maybe, I don't know, a few minutes to an hour. But this is where the real engineering discipline comes in. The pitfalls are real.
Right, which brings us to validation. Step 6. This feels like the step everyone wants to skip, but you're saying it's non-negotiable.
It's the most important step. You have to build a test suite that is specific to your domain. You're not just looking to see if the output seems okay.
You're comparing it to the original model.
You're comparing factual accuracy, reasoning on complex questions, even specific formatting. Like if you need JSON output, if the quantized model fails where the original one succeeded, then you have a quality problem.
And then there's the configuration management headache. The tool spits out the weights, but also all these little config files.
The config.json, the quantized.config.json.
And the warning here is?
The warning, based on a lot of pain from a lot of developers, is do not touch those files. Don't edit them manually.
Why not? They look like simple text files.
Because you are effectively breaking the precise math, the scaling factors that the process created. It's the #1 cause of corrupted models that seem fine, but then produce catastrophic failures later. Save everything together as one unit.
What's the most common reason the quantization process itself just fails?
Out of memory. Ooh, but, and this is the crucial part, it's O during the quantization, not during inference later on.
And that's because it has to load the full precision model first?
Exactly. It loads the whole FP16 model into VRAM to work on it.
Yeah.
If you hit that wall, the fix is usually simple. Reduce your number of calibration samples, maybe from 512 down to 128, or lower the sequence length you're using for calibration.
Okay, now let's talk about the bleeding edge. What happens when the standard methods, even AWQ, just don't work? You mentioned something about outliers,
Yeah, this happens sometimes with new model architectures. They can have what are called activation outliers.
which are
Think of them as huge, unexpected spikes in the numbers flowing through the model. When you try to squash that into a tiny 4-bit space, the math just breaks.
so what's the complex intervention for that?
This is where you might have to stack techniques. You might first apply a method called smooth quant.
And smooth quant does what?
It basically finds those big spikes and smooths them out, spreading the difficulty across the network. Then, after you've smoothed it, you can apply something like GPTQ to do the final 4-bit compression.
That sounds like some serious advanced MLOps.
It is. This is not a standard workflow. You only do this if the standard methods have failed you, or if you're one of the first people working with a brand new model. Always check the GitHub issues for the model first. Someone else has probably already hit this problem.
So we've covered the why, the how, the what to use, and the what to do when it breaks.
Right. The big takeaway here is that quantization isn't just a compress button you push. The real engineering is in the details, the calibration data, the clean environments, and the rigorous testing.
And that's what ensures you actually keep the intelligence while you shrink the footprint. When it's all done, how do we know if we've actually succeeded in a production system? What are the metrics for success?
I'd say there are 4 dimensions. The best quantized model balances all of them.
Okay, what are they?
1, memory efficiency, this shit your VRAM target. 2, infant speed, your actual request per second. 3, quality retention. Can it still do its job accurately?
And 4?
4 is stability. Does it run for hours, for days without crashing? You never want to chase the absolute smallest file size if it compromises speed, quality, or stability.
So if we zoom out one last time, all this work, all this complexity, what's the big picture impact of all this?
The big impact is accessibility. When you do this right, you stop worrying so much about hardware constraints.
It changes the economics.
It completely changes the cost structure of serving AI. You can take these massive, incredibly smart models that used to be trapped in million-dollar data centers, and you can deploy them on much more affordable, available hardware.
It really democratizes it.
It does. It lets sophisticated AI deliver value wherever it's needed, not just where the most expensive GPUs happen to be.